Hello, everyone, and welcome to today's webinar, Savings Simplified, a Guide to Fume Hood Energy Reduction. I'm Lexi Krause of LabRoots, and I will be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Labconco. To learn more, please visit their website at www.labconco.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. This webinar is educational and thus offers free continuing education credits. Please click on the Continuing Education window at the bottom of your screen to obtain your credits. I'd like to now welcome our speaker, Kasey Fulmer, Product Specialist at Labconco Corporation. Kasey, welcome. You may now begin your presentation.
Thank you so much for that introduction. Everyone, I'm Kasey Fulmer. I appreciate your time to be able to provide this webinar to you. This is a topic that is important to me, and I'm excited to share this information. Hopefully, you all will get quite a bit out of it as well. Today, we will be talking about the following subjects. We're going to discuss the brief history of fume hoods, where they started, how they've come along, and how they've gotten to where they are today. The energy savings developments that are available in fume hoods and how we've come to those, as well as the implementations of these options. Sometimes it's beneficial to have more than one energy saving option for your hoods or your building. So we'll be discussing all of this through this webinar, but we're going to start with the brief history of fume hoods. So fume hoods, the concept for the prevention of contact with hazardous chemicals goes way, way back. There are drawings and notes from alchemists that date hundreds of years before we came into contact with our first fume hood that shows these similar practices. We find more evidence of laboratory ventilation type implementation of practices in the Edison laboratories in the early 1900s. And so what they would do in those laboratories is they would actually perform their experiments in fireplaces. So the building would be warm and they would put their experiments in the fireplace, and the difference in pressure from the inside of the building to the outside of the building would carry the harsh chemicals outside. Really, whenever it was a hot day, they would put their experiments on the outside of the building, on the ledge of a window where the wind would carry those chemicals away. So we start to see a little more implementation of that type of protection in the Edison laboratories. The first modern fume hood is actually credited to the University of Leeds in 1923. Basically what it was a large cabinet. It was standing at working height and had a vertical rising sash, which was arranged like parallel windows. This is the first time it was kind of introduced as a sort of box type build. And then after that, fume hoods were commercially available since the 1930s. And since that point, the developments of fume hoods began. And for a while, after these were commercially available, everything was great. Fume hoods were working. People had a form of protection, and everyone was generally safe. Even in the 1940s, we saw massive jumps in fume hood technology, where things were developed back then that are still used in fume hoods today. Concepts like bypass air and VAV and things like that we'll touch on later in this slide were actually introduced in the 40s. So that's the brief intro to that part of the history of fume hoods. But then something happened around the 1950s, and that is air conditioning. So the concept of conditioning air, cooling air, has been around before the 1950s, but in the 1950s, air conditioning became more commercialized. It's more readily available. It was introduced in a lot of buildings. People had them in their homes. This was a new concept. And one of the concepts that comes with AC is that buildings then had to be closed. They had to be enclosed. So no more buildings with open windows or operating with open doors as they had done before. With these closed buildings, air then had to be supplied to the buildings, and that air was tempered. Keep in mind, laboratories today use what is called single pass air. So air in the room that I'm in, which is not a laboratory, the air is probably not considered typically expensive, as this air is recirculated. As it heats up, it's recirculated, cooled about 4 degrees, and then put back in the room to keep everyone comfortable. But in labs, that air comes in and then it exits. So AC in labs became very expensive as it pertained to fume hoods. So the tempered air would come in and the fume hoods would take that tempered air out. Just for a brief explanation of what happens to air as it comes into a building to be tempered, just to highlight the fact that it's an expensive process. Let's just imagine that outside it is 80 degrees. That 80-degree air doesn't just come in and get cooled to 70 degrees and expelled into the room. No, that air could have a substantial amount of moisture in it. And so that air needs to be cooled down to below 50 degrees to take some of that moisture out of the air. And then that now 50-degree air needs to be reheated back up to the 70 or 68-degree air that is pushing in the room, because you can't just push out 50-degree air into a room. People will be uncomfortable. This is quite the process to get the air outside to a comfortable working level in the laboratory. So all of this expensive air comes as a lab in the fume hood, having the lab being single pass air, takes that air and pushes it outside. And then the cycle repeats itself all day, every day, as long as the fume hood is on. There's this implementation of fume hoods and air conditioning at labs, and people who ran them noticed, man, these energy bills, the consumption by this lab is very, very high. Thus, the need for more energy efficient fume hoods was born. And so we're going to discuss today some of these options. First option I want to discuss is the auxiliary air fume hood. Now, these hoods were an innovative design at the time, and I wanted to cover it because these still come up in questions today. I still handle these types of calls, and so I wanted to touch on it. But it was a rather innovative design at its beginning. It was pretty clever. And basically what happens with these hoods is that the air enters the lab in two places. The first place being the typical supply air register that's in the lab, it's in every lab. And then the second, as you can see in these images, is right in front of the fume hood. You would take outside air, untempered, and expel it right in front of the fume hood. And the idea was that the air that was taken out of the lab would contain 70% of the untempered air. So if it's taking only 30% of tempered air out of the lab, and 70% is conserved, thus saving energy. It's a decent idea, but unfortunately, what happened with this design is that energy reduction was prioritized, but safety was sacrificed. There were a couple of problems with these hoods. The first being user discomfort. With these hoods, if you're looking at this image, the user of the hood is standing about where the word room air is, so that's the front of the hood. And if you can imagine a very cold day or a very hot day, which happens anywhere, that untempered air is blasting right on the user. So if it's 30-degree air, it's right on the user. If it's 110-degree air, the user's experiencing that as well. So the users got very uncomfortable working with these hoods whenever the outside air was less than desirable. The other issue was that, as you can imagine, untempered air, it has a lot of moisture, as we kind of discussed earlier. It comes into contact with the air of the room, and then all of a sudden, condensation forms. So condensation would form inside of that supply air register, and similarly to the expelling of cold air on the operator, water would drip on the users. And again, that is less than desirable whenever you are operating a fume hood. The last thing that would happen, and this is the most important thing, this is the primary reason why these hoods are not advised or even used anymore, and that is they had a lot of balance issues. So with these hoods, you have two fans. You have one fan on the supply air right in front of the fume hood, and then you have a fan on the exhaust air on the outside of the building, somewhere at the end of the duct run. If those exhaust fans were not perfectly balanced, they would tend to create this harmonic frequency where they'd be pushing the other in and out of the operating range, which ultimately leads to loss of containment. And loss of containment means exposure of the laboratory personnel to whatever was being contained on the inside of the hood. And that, as it pertains to safety, is completely unacceptable when it comes to fume hoods. So for that reason, these hoods are largely eliminated. They still exist because the life of the hood may have been expanded, well taken care of, and we are actually seeing these being replaced fairly often. And ultimately, this shouldn't be a one-to-one replacement. You shouldn't replace an auxiliary air fume hood with an auxiliary air fume hood. There are many industry standards that would state this, similar to, say, ANSI C95. But really what should be looked at is any of the following options that offer reduced airflows while maintaining safe operation, which is the ultimate purpose of a fume hood, is to keep people safe. It brings us to option 2. This option is the reduced air volume, or RAV fume hoods. And before we get into this, I want to define a couple of terms really quick, just in case these terms are new to anybody who might be listening. The first is face velocity, which is the speed of the air as it enters the fume hood face. This is measured in feet per minute, or FPM. And if you are having trouble kind of imagining that, it's a very similar concept to driving your car and how it is measured in miles per hour. So it's a speed in a duration of time. So it's a single point in a duration of time. The next term is volumetric rate, also sometimes known as airflow, but this is the amount of air that is being moved through the fume hood over a period of time. So the volume of air over a period of time, it is measured in cubic feet per minute, or CFM. These are directly related. Face velocity and volumetric rate are related with the equation that you see here. Q is the volumetric rate, V is the face velocity, and A is the area of opening. This is important because the effect of one of these variables affects the other ones. So, for instance, these hoods are typically used in a constant air volume system. A brief description of a constant air volume system is that no matter the hood condition, the same amount of air, CFM, is being pulled through it at all times. There is no modularity in the amount of CFM that's being pulled through it. So, as that is remaining constant air volume, the face velocity is actually changing, which is really how these reduced air volume fume hoods work. It's very, very simple. If you reduce the size of the opening that air is moving through, you reduce the amount of air that's needed to maintain a phase velocity. So if you refer back to that equation up at the top of the slide, you can see Q equals VA. If you reduce the area opening by half, based on just that equation, the volumetric rate also has to reduce by half by a combination of those things. So volumetric rate, less air being pulled out of the lab, less energy being used to temper the air that is being supplied to the lab. This exists in a couple of forms. One is simply just lowering the operating sash height. So instead of operating at the sash at, say, 20 inches, if you operated the sash at 10 inches, theoretically, your volumetric rate of exhaust of that tempered air would be reduced, not exactly half because fume hoods have bypasses, but very, very close. And a significant amount of air is conserved by doing that. These are very common practices. Another version of this type of hood is a combination sash. This hood has a sash that has 4 panes that move horizontally, all set in a frame that also move vertically. But with that sash in the down plane, using the hood through those the horizontal sliding of those panels means that opening is reduced, and thus, obviously, as we have discussed, the amount of air needed is also reduced. This is the first option still alive today in today's market, and most manufacturers will have a version of this type of hood or ways to accommodate that. The next option that is becoming more and more prevalent in the market today is high-performance fume hoods. High-performance fume hoods are designed to operate at significantly reduced phase velocity, so less air is being pulled through, while maintaining very high levels of containment, meaning they keep the stuff inside the hood at a very high level while having a reduced phase velocity. For the longest time, phase velocity was the standard of safety. The need was you need 100 feet per minute phase velocity, and that was what determined safety. That's not necessarily the case with these high-performance fume hoods, which is a definition that's provided to us, to the industry, by SEPA. SEPA is the Scientific Equipment and Furniture Association. This definition is the widely accepted definition for high performance, and it is a performance-based definition. If a fume hood is able to perform or contain to a certain level on an ASHRAE 110 test with a phase velocity of 60 feet per minute and the sash entirely open, it can be considered a high-performance fume hood. These hoods are a great option for energy reduction because if you have a lower phase velocity, if you remember that previous Q equals VA, if you have a smaller phase velocity, that CFM that's required to pull that through the hood is significantly less. But how do they do these? What about these hoods has been done to allow such containment at such low phase velocities? Well, it's essentially attributed to performance features. Performance features like optimized baffles, which are at the back of the hood, which direct the hood airflows directly away from the user's breathing zone. They utilize airfoils, which are for smooth air at the bottom of the opening. There's curved profiles on the side and tops of the fume hoods, and everything is designed so that air is very smooth as it enters the face of the hood. There are many other types of performance features that are on these hoods, but the ultimate goal is to minimize turbulence. Turbulence in a fume hood means potential loss of containment, and that just will not do. And the benefit of this is that you have a hood that you are operating and being safe while doing so, and as well, reducing the amount of energy that is associated with moving that air through the hood because you're using less air. But how much less air? Let's quantify that a little bit. So this is an example. Everything is relatively arbitrary here, but I tried to keep what is similar constant as well. And I have this outlined in terms of dollars. There's not a great metric for energy reduction that everybody understands, but most people understand money, and so I have done the analysis in terms of money. So in this example, we are comparing a conventional fume hood, which would operate at 100 feet per minute, as had previously been the standard of safety. And we have a high performance fume hood, which operates at a 60 feet per minute phase velocity. So these hoods that are compared, both of them are 6-foot fume hoods. They each have an 18-inch working sash height. And what we have done here is we have standardized the cost of CFM per year. So you can see a note beneath the table where we say the cost of CFM can range widely from $5 to $13 per CFM per year, depending on location. If you have a really hot location and you have a really cold location, the cost to deal with the amount of air exhausted can vary widely. So we typically choose the $7 range for that, but it's a constant throughout this presentation. So it outlines the benefits here. As I have stated, the conventional fume hoods have 100 feet per minute phase velocity, which equates to about 800 CFM, maybe a little bit more, depending on the type of hood, maybe a little bit less. But the general concept is there. And then the high performance fume hood at a phase velocity of 60 feet per minute requires only 475 CFM. And you can see just by looking at those numbers what we're going to see on this table. Conventional fume hoods, I have yearly operational cost, 5-year operation cost, 10 and 15 as well. And this is going to be constant throughout the presentation that you'll see. And ultimately, you see over 15 years, running the same exact hoods, you're doing the same thing, except for at a reduced phase velocity. And just by choosing high performance fume hoods and making sure that your application allows for the use of lower phase velocities, you save $2,270 a year, or $75 a year, just by choosing a high performance fume hood and making sure it works with your application. Over 10 years, $34,000, that fume hood has likely paid off itself. Keep in mind, this is just one fume hood. If you have multiple, as we will look later in this presentation, the benefits begin to compound. Okay, so that's high performance fume hoods. That's another option. The next option I wanted to discuss is a variable air volume system. This is a little bit different. The previous options have been exclusively about the fume hoods themselves, but for this option, it is related to the mechanical system that the hoods are operating on. So the variable air volume system, we discussed the constant air volume system. Well, the variable air volume system is essentially the counterpart of the constant air volume system, or CAV. So in a VAV, air is modulated based on how high the sash is, and the thing that's kept constant in a variable air volume system is the phase velocity. How they do this is there are typically controls on the fume hood, sensors on the sash that are relaying information to a controller, which are then relaying information to a valve in the duct run. And these are highly calibrated instruments that know exactly how much air they need to modulate through the fume hood to make sure that a phase velocity is maintained. This is a great application of this type of energy reduction. Essentially, you maintain a level of safety here, because when fume hoods are shut, they really should be left on. There are a lot of industry standards that would suggest that the continuous operation of a fume hood is the safest way to operate a fume hood, because it allows you to maintain a negative pressure in the fume hood as it relates to the lab. It also helps a lab maybe maintain negative pressure as it relates to other rooms, keeping directional airflows and things like that the way that they were designed to be, and ultimately just keeps people safe. So this increases the benefit of keeping the sashes closed, or keeping the hood on when the sash is closed. I apologize. Because less air is going to be drawn through whenever that's happened. A lot of times in these scenarios, nobody's using the hood. The VAV system has a minimum turn down, and then when the hood is in that position, it automatically goes to that turn down level. And then finally, the design face velocity is maintained most of the time, or it should be all the time. A risk assessment's done in a lab, and decisions are made for what is needed to maintain safety for laboratory personnel or equipment in the lab while the hoods are being used. And one of the outcomes of that risk assessment is what face velocity is needed to maintain safety in the hood. Well, if the face velocity is not changing as the sash is moving, as opening is getting bigger or smaller, that face velocity, which has been decided on, it doesn't change. And this is a very, very complex system that allows this number to be maintained quickly. The main downsides for this type of system is that the startup costs can be higher than typical installations. That's because the equipment associated with it is an extra to what would be a typical constant air volume system. And for this reason, most often they are beneficial on multi-hood installations. They can be used on single hood installations, and they are, but a lot of end users notice the energy reduction benefits whenever they're installed on multiple hoods. So let's take a look. Let's quantify the energy savings here. Again, this is done in dollars. For this example, let's outline the constants that are the same between the constant air volume system and the variable air volume system hood. They are each a 6-foot hood. They are operating at 18-inch working sash heights when they are in use. The face velocity is going to be 100 feet per minute for each of them, and the same cost per CFM. What is different about the constant air volume hood is that the hood is always on, and it is always operating at 800 CFM. So no matter what the hood is doing, wherever the sash is, that hood is pulling, or the exhaust fan is pulling 800 CFM through that hood. The variables in the VAV hood is that it has operating hours and non-operating hours. So for this example, I chose it's operating for 8 hours a day, and it's not in use for 16 hours a day. Assume 7 days a week. So the average CFM, so if it were to operate at 800 CFM when it was in use and 200 CFM when it was not in use, would be the same thing as running that hood at 400 CFM all day. And immediately, just by noticing that the constant air volume hood is pulling 800 CFM all day, you'll notice that it is half as expensive for the hood on the variable air volume system. It's not necessarily about that. It's about half of the air that is needed to supply for these hoods is being exhausted. You are exhausting exactly half of the amount of air on this hood, so all of that energy is conserved. It's an obvious depiction of energy reduction, and it's a great option that many are using today, and it's becoming more and more prevalent as we go along. The next option, and really the last option before we get to combining some of these, is ductless fume hoods. These are, as far as fume hoods are concerned, these are relatively new concepts. They are becoming more and more acceptable across the market. They are gaining traction and popularity. When focusing on energy reduction, it's really impossible not to see the impact with this type of fume hood, because it has 100% recirculating air. So all of the air that goes into the hood is put back into the room. There's no ductwork. There's nothing associated with tempering the air that is moved through this hood. It's important, though, that you understand that these hoods, when operated correctly, can still be a safe option. They will have a carbon filter or some sort of media. Carbon's just the most popular. That as hazardous fumes are coming through those filters, the chemical is captured, and then clean air is recirculated into the lab. So nobody in the lab is exposed. The hoods aren't consuming tempered air. The overall impact on the building is substantial, and the benefits are rather large. One of them being it is completely independent of a mechanical system. It does not matter where the ductwork is located. It does not matter if the building happens to be really, really tall and you need new ductwork for a ducted hood. These hoods can operate there. They're good for that, especially when looking for energy consumption reduction. No exhaust air means no supply air. So if you're not taking anything out, you don't have to put anything back into the lab as it's associated with this hood. You still have to do that in a lab, as we had mentioned, with single pass air, but as it's associated with the fume hood, and that's what we are addressing here today, there's virtually no air associated with that, which means all energy that is associated with exhausting air in fume hoods is entirely conserved. It's a big deal, and it's a great option, especially for energy-starved labs that don't have the capacity to have a ducted fume hood. And the main downside with the ductless fume hood is that there are limited applications when you compare them to a ducted fume hood. However, manufacturers of these types of fume hoods across the entire industry will supply some sort of application review. So you'll get verification essentially from the manufacturer of the hood or filters that your application is compatible with them, but the amount of applications is reduced as it's compared to ducted hoods. But let's take a look at what this means as far as quantifying the energy savings. And I went ahead and just compared it to a high performance fume hood. Because you can imagine the savings are going to be substantial. It is modified just a little bit because the previous example assumed the energy required to operate the systems were about the same between the types of hoods, but it's not exactly the same as it pertains to ductless fume hoods, which plug into a wall. The constants are the same, 6-foot fume hood, 18-inch sash height. I've explained all that. The high performance variables, we've taken a look at that, 60 feet per minute, 475 CFM. The one thing that we are adding here to this is it's about $800 a year for electricity to run the exhaust fan and other electrical portions of this type of hood. That's important because that's really the variable as far as energy consumption goes with ductless hoods. It costs about $1,000 a year for the electricity to run the fan modules associated with a ductless hood. And so that's really where we find the comparison here. You assume $1,000 a year for the ductless hood compared to the high performance fume hood, which is taking air out of the building and thus requiring supply air. And this is one fume hood, just like the other examples are showing, that over 15 years, the net savings is rather substantial at $46,000. Again, this is a generic example, but it does highlight the amount of energy that's conserved by using a ductless hood instead of a ducted hood when the application is suitable. So these are primarily the main options that are out there, but that doesn't have to be used independently of one another. I've got a couple of options here where I combined a couple of concepts, and we'll take a look at them. The first one that we are going to discuss is using high-performance fume hoods on a VAV system. So this is a great opportunity here because this type of lab is becoming very, very common. So let's set up a hypothetical lab. Let's make some assumptions here. We're gonna put 10 fume hoods in this lab. All of them are going to be 6-foot fume hoods. To address the VAV system, there's going to be time when the hood is in use and when the hood is not going to be in use. This slide, one assumption we have to make is that a chemical hygiene officer for this facility has done a thorough risk assessment, and then they have determined that these phase velocities when the hood is in use and the amount of CFM when the hood is not in use are perfectly applicable to what they need to keep the lab protected, laboratory personnel or equipment protected. So they have determined that for whenever they're in use, 60 feet per minute or exhaust flow rate of 475 CFM is perfectly acceptable for the use position. When they're not in use, there are some hazards that they need to make sure that they need to keep 200 hood air changes per hour flowing through those hoods, which is about 135 CFM. Other variables that are included in this hypothetical lab is that these hoods are used 10 hours a day, 5 days a week. We're going to be nice in our hypothetical lab. We're going to give people off the weekends. We're just nice like that. So what the result here is you have the hoods running at 475 CFM for 10 hours a day during the week and 135 CFM for 14 hours a day and 24 hours a day during the weekend. Essentially the same thing as running the hoods all day, every day at about 240 CFM. It's a reduction you can clearly see here. Let's take a look at what this does when compared to other hoods on other systems. So we have in the left column 10 conventional hoods. So these are just standard fume hoods. They are operating at 100 feet per minute all the time. They're on a constant air volume system, and as you can imagine, $840,000 is no small number for these 10 hoods to be operating at. The cost just associated with moving air through these fume hoods. The other comparison that we have here is if you just took those 10 hoods and you turned them into high-performance fume hoods, you can see the reduction here. We kind of covered that in the high-performance example. I won't outline it here, but you can clearly see a reduction there. But if you have those same 10 high-performance fume hoods and you put them on a variable air volume system so that they reduce air as they are being shut, the energy savings are rather substantial. You go from 840 to 500,000 to then $250,000 to operate these same hoods in the same lab, just on a different system and a different quality. The savings are just incredible. So this offers multiple benefits. One, you have high incentive to maintain negative pressure in the hood. You have high incentive to keep these hoods on and maintain safe operation of these hoods even whenever the hoods are not in use. This is safe. You have an intuitive system that automatically accommodates for changing sash opening. So you don't have to worry about user input as it relates to maintaining. As they close the hood, they have to turn down the system or anything like that. The system just does it. And as we have seen, a massive reduction in energy consumption. So you are reducing energy, increasing savings, and maintaining safety, which are paramount when it comes to fume hoods. The other option I wanted to show or outline are whenever you combine high performance hoods and ductless hoods. Again, let's take this hypothetical. Let's take a new hypothetical lab, and we're going to look at it in a little bit of a different way. Still using 10 hoods. They're still 6-foot hoods. Your safety officer has determined that the ducted hoods need to run at 60 feet per minute, which means 475 CFM. I've said this many times now. Your lab space is 1,425 square feet, and the ceilings are 10 feet tall. So we've laid out the lab space. And after a thorough risk assessment, your chemical hygiene officer has determined that at no time should your lab have less than 10 room air changes per hour. So room air change is how many times the volume of air in a room, in a lab, is changed out with new air in an hour. So this has determined 10 room air changes per hour at all times, whether hoods are being used or not. What does this mean? So if you do a little bit of math that I am not showing on the screen, but if you do a little bit of math, you find out that to maintain those 10 room air changes per hour, you need to exhaust 2,375 CFM to maintain that 10 air changes at all time, which conveniently for this example happens to be the same amount of air that will be moved through 5 high-performance 6-foot fume hoods running constantly. So what does that mean? It means that if you have your high-performance fume hoods, you need 5 of them. You run it at that phase velocity that you have determined to be safe. You exhaust that 475 constantly. Your room is now safe because you've met your 10 room air changes per hour, and your hoods are operating at a condition that your safety officer has determined to be safe. This is great, because what does that mean for the other 5 hoods is that they can be ductless hoods. You don't need energy associated with moving through those hoods. As long as the application is acceptable with a ductless hood, these are essentially free hoods to the lab space. This is exceptional because you don't have to accommodate for additional exhaust running through these hoods. And your room air changes, your laboratory room airflows, your building airflow, directional airflows, all of that is maintained, and now you can have 5 hoods that are operating ductless. So let's take a look at numbers here with this option of using the high performance and ductless fume hoods in the same laboratory. We already discussed the 10 conventional hoods; those numbers are the same. We already discussed the 10 high performance hoods; those are the same. But then let's take a look at what happens when we combine them. These numbers, what you'll notice, are rather similar to the other example. They're almost half of what half of the energy consumption of the previous 10 high performance hoods, and almost a quarter of the conventional hoods. The reduction in energy is blatantly obvious. You're not moving air out of the building with the ductless hoods. You're moving significantly less out of the building with the high performance hood. You're getting the benefit of maintaining your air changes per hour that your safety officer has required for the safety of your building. The ducted hoods in the same lab space allow application versatility because they can handle the applications that might not be approved for a ductless hood. So you're able to perform everything that you need to. And then, as we have seen on many of these slides, there is a massive reduction in energy consumption of your laboratory. In this sense, you don't have the install of a VAV system, which can be complicated. So that is there's a minor added benefit. You're reducing your energy consumption, you're increasing your savings, and you're maintaining safety. Again, that's exactly what you're looking for with your fume hoods. So as you've seen from this presentation, there are many options for energy reduction as they are associated with fume hoods. And you don't have to sacrifice safety in doing so. I appreciate your time. I look forward to fielding your questions. Thank you.
Thank you, Kasey, for that informative presentation. We are now going to start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on that Ask a Question box located on the far left of your screen, and we're going to answer as many of your questions as we have time for. So Kasey, let's get started. Our first question is, what types of hoods are you referring to when you say conventional? Is it both auxiliary and RAV?
So when I say a conventional hood, it's more as it relates to the performance of a hood. With a high-performance hood, it's been proven to have exceptional containment properties, which allows it to be able to be operated at those lower face velocities. Conventional fume hoods, before the implementation of these high-performance types of features, typically we're only able to run at the higher face velocities, like 100 feet per minute, which was for a long time the standard of safety with fume hood operation. So when I say conventional fume hood, I mean a fume hood that has not had those high performance features added to it, in its operating at 100 feet per minute, because it hasn't been proven to be able to contain well enough at lower face velocities to be acceptable in that manner. It's a good question.
Great, thank you, Kasey. So our next question for you is, how does the required minimum air changes per hour for the laboratory affect the decisions on the best fume hoods to install?
Yeah, so I mentioned air changes per hour a couple of times during this presentation, and honestly, this question we could have an entire presentation on this question alone, and it'd be completely different than the one that I just presented. But ultimately, whenever a lab is being designed or decisions are being made with a chemical hygiene officer and implementation of a chemical hygiene plan, a thorough risk assessment is done on everything that needs to be avoided, contained, accounted for, to make sure that everyone in the lab, building, people using equipment, everybody's safe. And something that can come out of that risk assessment is directional airflows or room pressurizations of a building. And so to get that type of airflow, to get those types of directional airflows or pressurizations, air changes per hour is just sometimes a result of that. So if there's a risk present in a lab that requires a substantially higher room change per hour, and your hoods are exhausting a certain amount of air, it wouldn't necessarily, or there's a potential that it wouldn't necessarily make sense having high-performance fume hoods because, or sorry, not high-performance fume hoods, but having fume hoods that operate at lower face velocities, because you're going to need to exhaust a bunch of air anyway. Especially when thinking about a VAV system where you're needing more air changes per hour when the hoods are not in use. So it's more just of what you're going to operate the hood at, and if you have savings available, energy savings available based on the numbers associated with your air changes per hour.
Great, thank you so much, Kasey. So moving on to our next question. Did your cost of the ductless hoods include the filter costs? And do you know about the typical cost of these filters?
So the typical cost of those filters range widely, and I'm not sure I can really speak to that sense. But I didn't include the cost of the filters for the hoods because I also didn't include the cost of the maintenance for the ducted hoods. So we'd consider that a maintenance cost associated with those hoods. And for the sake of this presentation, it was exclusively about conserving energy, and I chose dollars to help quantify those numbers. Definitely, the ductless hoods have that added maintenance cost associated with them because ducted hoods do not have those. But as far as the reduction of energy consumption, I decided to leave that off because I didn't include maintenance in any of the cost comparisons in the presentation.
Thank you, Kasey, for that answer. So looking at our next question, okay, here's one for you. So when replacing an auxiliary air hood with one of these other options, what is the primary concern that should be addressed?
So with auxiliary air hoods, they're often in a building that was designed with an exhaust system that was sized to handle a reduction, or sorry, the supply air was sized to only supply a certain amount of air to the lab space. And if a new type of hood is being put in there, it needs to be able to operate within the energy capacity of the lab space. So ultimately, if the auxiliary air hood was operating with 30% of conditioned air that was supplied to the lab, the new hood should be able to operate within the supply and exhaust capacity of the existing mechanical system associated with it.
Thank you, Kasey. We want to thank our audience for all these amazing questions that are coming in, and we're just going to keep going with them. So our next one, are the filters used for ductless hoods recycled through a Labconco program, or are they to be disposed for incineration?
They aren't recycled through a Labconco program, but a lot of the suppliers of filters can provide some form of those services. Ultimately, the way that these are disposed of depends on local codes and certain requirements in municipalities. So ultimately, that should be something that should be looked at whenever considering purchasing one of those types of hoods, if it meets your needs and is a good option for your building.
Great, thank you, Kasey. Our next question, should high-performance hoods always be operated at 60 feet per minute face velocities?
So I chose 60 feet per minute because that's the standard that we've been provided that is required of a high-performance fume hood. So to be considered a high-performance fume hood, you need to perform at a really high level on an ASHRAE test at 60 feet per minute. So those hoods are proven to have excellent containment down there. However, it's really an application by application basis. You really need to evaluate what you're doing inside the hood and determine if your application allows for the reduction of face velocity based on what you're doing, how you're doing, whatever your process is, SOPs of your building, various things like that. Sometimes those types of answers are existing within a lab's chemical hygiene plan already.
Thank you so much. And it looks like we've got time for a couple more questions. So what is the risk in simply turning off the fume hoods when they are not in use to conserve energy?
Yeah, that's a good question. And ultimately, there are industry standards that point to reasons why we don't recommend turning off hoods, and it's ultimately because the risk associated with that is risk associated with a lot of things, and that's misapplication or misuse of hoods. So, for instance, a typical industry, an industry standard that exists, and I mentioned it in the presentation, is ANSI Z95, and they supply guidance on what you should do before you're able to turn off a hood. And one of those, and it is to have the hood completely decontaminated and cleaned, and then backdraft prevention is needed in the ductwork. So the risk is there that somebody who's using the hood did not completely decontaminate the interior hood. They forgot to clean up something that still has residual hazardous chemicals on it, or it has a dish or something that wasn't fully cleaned out, and you turn off the hood, and all of a sudden you have something just sitting in the lab off-gassing hazardous fumes and vapors, which can affect equipment in a lab, the hood itself, as it could be potentially corrosive. Also, if there's no backdraft prevention in place and the hood just gets turned off when maybe all of the vapors haven't been exhausted, if there's a difference in pressure between the room and outside, that those chemicals could actually be drawn back into the lab space. So having the hoods always on is safe because it keeps everything under negative pressure. If anything was not done correctly, you can ensure that if there's residual chemicals, that it's being taken out of the building and not lingering in the lab space, keeping everybody safe.
Thank you, Kasey, for that answer. So it looks like we've got one or two more questions here. So looking at this one, since the ductless hoods aren't connected to a mechanical system, can a customer move the hood from room to room to cut down how many fume hoods they need to purchase?
Yeah, so the answer to that one is likely not, because there's a couple of issues with that. Whenever a hood is put in place, it's certified there. It's tested or should be tested and certified in the location that it's in. If you're moving a hood from room to room, the conditions are entirely not the same, and there's no guarantee that the hood will be placed next to a door or an air supply register or something like that, which may affect the performance of a hood in a way that is not acceptable or wouldn't be acceptable if it was tested in that new space. Anytime a hood is moved or repurposed or anything like that, it should be recertified before it's used. And if you're moving it daily or weekly or even monthly, it's typically not economical to have to do all that certification over and over again. So that's the main reason. Other reasons is oftentimes these hoods have service fixtures connected to them, which is hard plumbing. So if there's water connected to it, you wouldn't be able to move the hood. If it's got electrical connected to a duplex, you wouldn't be able to move it without disconnecting those spots. There are other smaller enclosures that might be better off used for that type of application.
Thank you so much, Kasey. And it looks like that is the last question that we have time for today. We want to thank you, Kasey, for your time and your important research for this presentation. We would also like to thank LabRoots and, most importantly, our sponsor, Labconco, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions that we did not have time for today and those submitted during the on-demand period will be addressed by our speaker via the contact information that you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, bye-bye, everyone.